Welcome to The Explainer. Today we're breaking down one of the biggest buzzwords to hit the AI world in a long time, the 1-bit LLM. Now on the surface, it promised this huge leap in efficiency, but the truth behind the marketing is actually way more clever, and it reveals a deep secret about how to build AI that's not just smaller, but smarter too.
Okay, so let's get right into it. When Microsoft dropped the term 1-bit LLM, it was, a marketing masterstroke. The idea of an AI model that runs on just a single bit for each of its parameters, that sounds like a total revolution in efficiency. But was that the whole story?
Well, here's the twist. The name itself kind of hides a really fascinating technical detail. Because if you actually dig into the research paper, you find out that 1 bit is more of a clever metaphor than a literal nuts and bolts description.
Yeah, the number that actually matters isn't 1, it's 1.58. The model is really a 1.58-bit model. And that just immediately makes you go, wait, what on earth is a fractional bit? How do you even store that in a computer's memory? We're going to unravel that mystery, I promise. But first, we need to understand why you'd even want to put an AI on such an extreme diet in the first place.
So before we get into the nitty-gritty of how this works, let's talk about the why. The motivation behind this crazy compression isn't just some academic exercise. It's super practical and could totally change how we all interact with AI.
The ultimate goal here is to take these massive cloud-based AI models and get them to run directly on your phone or your laptop. When you shrink the model's weights from, say, 16 or 8 bits all the way down to just under 2, you absolutely slash its memory footprint. And what that means for you is faster performance, way smaller downloads, and this is the big one. It means powerful AI can finally operate locally, keeping all of your personal data private and secure on your own device.
And the performance gains? They're staggering. Look at this. These aren't theoretical numbers. On real hardware, BitNet runs its tasks up to 9 times faster on GPUs and 6 times faster on CPUs compared to traditional models of the same size. That is a total game changer.
So how does this all actually work? Well, the core idea is surprisingly intuitive. It actually takes its inspiration from a really simplified view of how the human brain works.
The whole philosophical starting point, which Bill Gates actually talked about, is that a neuron in your brain is basically a binary switch. It either fires or it doesn't. It's on or it's off. And this simple on or off concept is the foundation for simplifying all the weights inside an artificial neural network.
Now here's where the real magic starts to happen. Early attempts at this used what we call binary weights, just a simple choice between -1 and +1. But the real breakthrough, the thing that made this all click, was moving to ternary weights, which introduces this incredibly powerful third option, 0.
That 0, that's the secret ingredient. Having a weight of 0 lets the model completely tune out parts of the input that it decides are irrelevant. It's like giving the model an ignore button, which makes it way more efficient. And of course, if you want to store 3 distinct values, -1, 0, and +1, you need a little more than 1 bit of information. How much more? Log base 2 of 3 to be exact, which is exactly where we get that magical 1.58 bits from.
Okay, so you've got this cool idea, but how do you actually jam it into a massive large language model without having to redesign the entire thing from the ground up? Well, the answer is surprisingly elegant. The way they implemented this is just incredibly clever. Instead of rebuilding the whole architecture, the engineers just swapped out one single standard component. In a typical AI model, you have these things called linear layers. They're basically just doing big matrix multiplication. They replaced those with this new custom bit linear layer.
So think of this new layer like its own little self-contained machine. It takes in the regular, full-precision numbers, stabilizes them, and then it squishes them down to 8-bit integers. Then it does the super efficient multiplication with those ternary weights we talked about. And finally, it puffs the result back up to full precision before passing it along. The rest of the model has no idea anything even changed.
But just swapping out that layer is only half the story. You can't just plug it in and expect it to work. You have to train the model in a very specific way. And this is the real secret sauce that brings it all together.
Normally, you might think you could just train a model fully and then try to shrink it down afterward. That's called post-training quantization, but it totally falls apart when you get down to these extremely low bit widths. So instead, BitNet uses what's called quantization-aware training. It's basically like exposure therapy for the model. You force it to deal with its low-bit, quantized reality during the entire training process, so it learns how to work within those tough constraints right from the very beginning.
Now, to make that training actually work, you need a legendary hack from AI pioneer Geoffrey Hinton. See, the problem is that AI learns by taking tiny steps up a smooth hill to find the best answer. But the math of rounding numbers turns that smooth hill into a series of sheer cliffs, so the AI gets stuck. The straight-through estimator is this brilliant trick that basically builds a fake ramp over the cliffs. It tells the model, hey, just ignore that messy math and pretend it's smooth, and you just keep on climbing. And against all odds, it actually works.
Okay, so the tech is fascinating. The engineering is super clever. But let's get to the bottom line. The question you're probably asking is, are these models actually any good?
So, the initial tests of the small, publicly available model weren't exactly glowing. When people compared it to giant models like GPT-4, its answers could seem, well, lazy or repetitive. But that's kind of like comparing a go-kart to a Formula One car. It's just not a fair race.
The real test is putting it up against models in its own weight class. And here, as this table shows, BitNet is surprisingly competitive. It totally holds its own against models of a similar size from Llama and Gemma. And what's incredible is that it's doing that while using a 6 times smaller memory footprint. That's pretty wild.
And here's the most important part. What we can test today is just the small, open-source version. The research is really clear that for these models, performance scales directly with size. They get a lot better as they get bigger. So that means the unreleased 70 billion parameter version that Microsoft has been talking about is likely a completely different and way more powerful beast. Which leaves us with a final, pretty provocative thought. We are seeing the very first steps of a technology that can take massive, cloud-scale AI and put it directly into our hands, running privately on our own devices. So the question is no longer if this is going to happen, but when.